start. We start. We start.
When you make it, come check the TV first.
They give you instruction. So join for online. Start. No, come.
When you make it, check the TV first.
No, and they give you instructions.
No, I didn't talk to you. If you make it, just right before
You
you
will
start.
come. You will come.
No, it's not about it. Come. If I know how to use,
You see.
don't be simple. I'm sure. If you know,
Unless we join.
hello. Hello. My name is Daniel Kobina Asanyaku. I am a second year geological engineering student, and today I'll be covering rectification in basic electronics. So, what is rectification? Rectification is the process by which AC current is converted to DC current. Now, why is this necessary? This is necessary because most of the appliances that we use at home, our fridges, our laptops, our phones, can all require DC current to function. However, the supply of current to our homes is AC current, or the current that is supplied to our homes is AC current. So therefore, there must be systems in place to convert this AC current that is supplied to our homes into DC current for our various appliances to work. There are two types of rectification: half wave okay. Hey. Half wave rectification and full wave rectification. Now, in half wave rectification, a transformer is employed to step down the supply voltage. No, let's do that. In half wave rectification, there's a positive half cycle and a negative half cycle. Half wave rectification is the type of rectification where So in half-wave rectification, the circuit is a single diode and a load resistor. So this is a circuit of a half-wave rectifier. Sorry for the bad habit. So in half-wave rectification, a transformer is employed, and the circuit includes a single diode and a load resistor. So this is the diode and this is the resistor. And in half-wave rectification, it produces a pulsating DC output. A pulsating DC output. So a pulsating DC output is a DC output where the DC has or current only flows half of the period. So a sine wave with the negative part cut out, basically. So this is what I've drawn so far, the positive half cycle. This is where current will flow. So in the positive half cycle, current peaks, like this is that's where current will peak, and that's where current will flow. That's how the flow of current will be documented. And so when current goes positive in the forward bias, it flows, and when it's reverse biased, or the path that aren't shown, current doesn't flow. So during the negative half cycle, the current is reverse biased, and the diode acts as an open switch. Now we know that when a switch is open, current doesn't flow. And during the positive half cycle, the ideal diode is forward biased. Here acts as a closed switch. Now, which means it took the load resistor, as I previously shown in the circuit before. The load resistor, current will be flowing to the load resistor in the positive or in the forward biased half cycle, or in the positive half cycle. So the output waveform of a half-wave rectifier is like what I previously demonstrated. A sinusoidal sine wave, or sinusoidal wave. Sorry. Okay. With so here okay. So this is the output waveform of a half-wave rectifier. the output waveform of a half-wave rectifier. So the source voltage will be in this manner, and so will the output voltage. And so the output voltage, only the positive half cycle will be shown in the output voltage. So as you can see here, the negative half cycle has been removed from the output voltage. This is known as a pulsating DC voltage, where an AC input voltage. Now, we know that AC is the abbreviation for alternative current, which is a current where current flows in the positive and the negative in a sinusoidal manner. So where current flows in the positive and the negative in a sinusoidal manner. But in half wave, only the positive half cycle's output is presented. So the negative half cycle input is removed from the output voltage. So in the output voltage, only the positive half cycle. Now, if the DC voltmeter is connected, if a voltmeter is connected to the circuit to measure the output voltage of the half-wave rectifier, we'll end up knowing that the DC output voltage, or V average, or V average, which is equal to V DC. Will be equal to 1 over T, the integral of V naught dt. 1 over T multiplying the integral of V naught dt. And with upper limit T over 2, or the half period, and lower limit 0, which is equal to 1 over 2 pi multiplying the integral of Vm sine omega t d omega t, sorry, with the, which is also equal to, if you integrate sine omega t, you get negative cos omega t. So Vm over 2 pi, negative Vm over 2 pi, negative, multiplying the negative cos of omega t. Now, if we put the limits pi and 0 into this equation, put the limits pi and 0 into this equation, we'll have V average, or V DC, or V of DC, V average V average, we have V average is equal to Vm over 2 pi multiplying negative cos of pi, obviously, minus because that's negative, cos of 0. Now cos 0 is 1 and cos pi is half. Cos 0 is 1 and cos pi is negative 1. So that would be V average is equal to Vm over 2 pi. Obviously, negative of negative is positive. So 1 plus 1. And that's 2. So the 2's to cancel out and we end up getting Vm over I. Now if we do the same thing for I average, we also attain Im over pi. We do the same thing for I average. It will be the same result of Im over pi, where I average is the average current passing through the load resistance. Now, do you remember the output V naught? It was in there. If you like to scroll down, V naught, yes, that's what we right here. So V naught here is the DC voltage plus a ripple voltage. So the output V naught is DC voltage plus the ripple voltage. That's something for you to keep in mind as you are solving your question. Now we need to find the root mean square. Now that we know the average value of the voltage, we need to find the root mean square of a half wave voltage. Root mean square or RMS value of the half wave voltage we need to prove. So that now I of root mean square is equal to the square root of 1 over 2 pi multiplying the integral of with upper limit pi and lower limit 0 Im square sine omega t square d omega. Now, first thing first, we are going to have to simplify what's inside the square root. And if you simplify, and you know that I sine square of omega t is also half of 1 minus cos 2 omega t. That's identity. It's an identity. So if we apply this into our equation, we can simplify it further to give us I of root mean square is equal to if you apply the identity, you're going to write I of root mean square is equal to the square root of what we have there and replace the sine square of omega t with half of 1 minus cos 2 omega t as stated in the identity. Now, if we solve this further, we end up with I of root mean square is equal to Im over 2. You can further simplify and solve it to know why it ends up like this, but due to time, and the form of your medicine, we will not be going into detail. Now, this also applies to the root mean square value for voltage. So voltage root mean square is also equal to 0.5 Vm or Vm over 2. Now let's move to peak inverse voltage of a half wave rectifier. Now, peak inverse voltage can be defined as the maximum amount of reverse bias that a diode will be exposed to. It is the maximum amount of reverse bias that a diode will be exposed to. Now, for a half-wave rectifier, it is simply for a half-wave rectifier, PIV or peak inverse voltage, PIV is equal to Vm. Now, the reasoning for this equation is that when the diode is reverse biased, there's no voltage across the load. Therefore, the secondary voltage, Vm, is what will appear across the diode. So, the maximum voltage or the maximum amount of reverse bias will be the same as the secondary voltage. Because since there's no voltage, only the secondary voltage will be what will be applied across the diode. Now, PIV is important because it helps us to determine the minimum allowable value of reverse voltage for any diode that we can use in the circuits. So, if you wanted to know the minimum amount of reverse bias to allow for a diode, so that our diode does not malfunction, for our diode not to malfunction, we need to know that value, the minimum amount of reverse bias that we can allow for a diode to be used in the circuit. Now, that value is simply the secondary voltage or Vm. So that's what PIV helps us determine. Now we move on further to the efficiency of a half-wave rectifier. The efficiency of the half-wave rectifier, aka the efficiency of the half-wave rectifier, which can be defined as has the symbol of this is the symbol for efficiency. So efficiency is simply the ratio of output DC power to input AC power. So we know that the purpose of a diode, the purpose of a rectifier, sorry, the purpose of a rectifier is to convert our input AC power into an output DC power. So the efficiency of the rectifier will be how well it converts our input AC power to the output DC power. And the way we can measure this is by dividing our output DC power by our input AC power. Now our output DC power equal to I of DC power is I square R. So the I of DC squared multiplying R for the resistance all over our input AC power. Now our input AC power is the I of the root mean square value of the current squared multiplying RF plus R. Now we know that RF is the forward resistance of a diode. RF is the forward resistance of the diode, and R is the resistance or the load resistance or the resistance of the load. So RF is the forward resistance of the diode, which is considered, and then R is the resistance of the load or load resistance. So whenever you are calculating input of AC power, make sure that you don't forget your forward resistance. It's sometimes overlooked and it is important. Now for maximum efficiency, our RF should normally be negligible, because the more forward resistance you have, the less efficient your rectifier is. So for the peak efficiency or for maximum efficiency, you should hope that your RF will be 0. Now when you go further into the equation, you realize that the efficiency or I of DC as previously stated, or I average, is equal to Im over pi, as we previously stated when we derived the equation for IDC. So IDC is equal to Im over pi, and I of root mean square, which we just found recently or a few minutes ago, is Im over 2. Now if we input this into our equation, for efficiency, if we substitute this into our equation asterisk, we will get the efficiency to be Im over pi all squared multiplying R all over Im over 2 all squared multiplying the sum of our forward resistance and our load resistance, or R. Now if you were to solve this, you will end up getting something like the efficiency. You end up finding out that the efficiency is equal to 0.405 over 1 plus our RF, or our forward resistance, over our load resistance. Now normally when the forward resistance is negligible, or when we are looking for maximum efficiency and the forward resistance is negligible, then, so for example, if I made forward resistance negligible in this equation, I'll end up getting our efficiency to just be 0.405 over 1, since 0 over R is 0. Which means that for a half-wave rectifier, the maximum efficiency is 0.405 or 40.5%. Our maximum efficiency is 0.405 or 40.5%. Now, it's very clear that 40.5% is not a sign of a good or a very efficient rectifier, which is why half-wave rectifiers are scarcely used. So, some applications of half-wave rectifiers will be a two-position lamp dimmer, or something that we use to charge batteries. Like half-wave rectifiers, due to their inefficiency, they are not widely used in electronics, but they are used in a few things, like what I stated previously. A two-position lamp dimmer. So some applications of the half-wave rectifier are a two-position lamp dimmer. So for those who prefer their lamps to have variants of dimming, not just on and off, they won't have a spectrum of light from dark to light. Half-wave rectifiers are used, and they can also be used in battery chargers or to charge batteries. Now, half-wave rectification has half-wave rectification has its advantages. It has very few advantages, but it has its advantages. And the advantage is that it's a simple way to reduce power to a resistive load. It's much simpler than full-wave rectification and bridge rectification, which we will get to. But its advantage is that it's a simple way to reduce power to a resistive load. So whenever you are questioned about the advantage of a half-wave rectifier, this is your go-to option. Now, it has a lot of disadvantages, including obviously the current is pulsating, and it only delivers power half of the time, so it's not necessarily the most efficient and most advantageous tool. Now let's solve an example. A 50 a 50 a 50 omega load resistance is connected across a half wave rectifier. And the input supply voltage is 230 volts root mean square at 50 hertz. Now we are told to find four things. We are told to determine four things. The first one being the DC output, which, as we have previously stated, is the average voltage. The peak to so if you want to find the DC output, we first have to find the secondary voltage. But first things first, let's draw the circuit. That's an important thing to always do before you progress in solving your equation. Be sure to draw a circuit. So that's our circuit right there. Now we can get to solving the equation. So this is our circuit with our rectifier or diode. A rectifier is simplified by a diode. Our load resistance and our volts. So first things first, when you are solving for this, we know that our V average, as previously determined, is Vm. Our V average is Vm over pi. V average is Vm over pi. Now we don't know Vm, but we do know our input supply voltage. And from previous lessons, Vm, we will know that Vm is equal to our input supply voltage root mean square, or V of RMS, multiplying the square root of 2. Now here in our question, our V of RMS is 230 volts. So our Vm will be 230 root 2. This will give us 325.3 volts. Now that we have our Vm, we can now calculate our V average, or our DC output. Which we previously stated is Vm over pi, which means 325.3 over pi. This will give us 103 0.5 volts. Now what we need to calculate next is our peak to peak ripple voltage. That's what we need to calculate for next. Our peak to peak ripple voltage. Now your peak to peak ripple voltage is the difference between your maximum and minimum in the V0 waveform. Your maximum and your minimum in the V0 waveform. This is giving us V peak to peak is equal to Vm, which is your maximum, minus your minimum. But here our minimum is 0. Hence our peak to peak zero volts. Our peak to peak will be equal to Vm, which is equal to 325.3 volts. So that's our peak to peak ripple voltage. Now we need to find our percentage ripple. Our percentage ripple. Now our percentage ripple is equal to V of peak to peak, or the peak to peak ripple voltage, all over our V average, or our DC voltage. Now our V of peak to peak was 325.3, and our V average was 103.5. Now we multiply this times 100%, and this will help us attain 314%. That shows you how much ripple is in half-wave rectification. There is so much of the ripple effect in half-wave rectification, which we know is a disadvantage of half-wave rectification. Now, what we'll calculate next will be our output ripple frequency. Now, in half-wave rectification, your output ripple frequency is equal to your input ripple frequency. Your output frequency, ripple frequency, is equal to your supply ripple frequency, or your input ripple frequency. Hence, our output ripple frequency Fr is equal to 50 Hertz. Now, from all that we have done, we can tell that, first of all, our percentage ripple was 314%. That is grossly undesirable. You do not want to have that much ripple in your current. Now, this ripple can be reduced by adding a capacitor across the load resistor. So we can control this ripple by adding a capacitor across the load resistor. Now this capacitor will help us to filter the voltage, producing a much more desirable effect. So that's just something to keep in mind for the future, that when halfway, due to the extreme ripple effects on halfway rectifiers, a capacitor is used to filter the voltage, producing a much more desirable effect. Now, I would like us to move to full wave rectification. But before that, I want to ask to note a few things. Note that in our calculations for half wave rectification, our diode was ideal. And an ideal diode is where current only flows in forward bias, and doesn't flow in reverse bias. So that's an assumption that we took when we were solving for our half wave rectification. In a practical diode, our barrier potential is taken into consideration. Hence, the output voltage will have a peak value that is less than the peak value of the input voltage, or 0.7 volts less than the peak value of the input voltage. So keep this in mind, that in a normal practical half-wave rectifier, your output voltage will always have a peak value 0.7 volts less than your input voltage. This is due to the barrier potential, which you learned about in semiconductors. Aside from that, the resistance of the diode also may contribute to the voltage in accordance with Ohm's law. So keep that in mind. Contributes to the voltage in accordance to Ohm's law. So those are just some things you have to note as you are about to write your matrix. Now let's move to the full wave rectification. Full wave rectification. Now, a full wave rectifier is one where current is conducted in both the positive half cycle and the negative half cycles of our AC output. Of our AC input. Now there are two types of full wave rectifiers. There's the center tapped full wave rectifier and the bridge. Today we'll be covering the center tapped full wave rectifier. Today we'll be covering the center tapped of the full wave rectifier, center tapped full wave rectifier. And if there's more time, we'll venture into the bridge rectifier. Now the center tapped rectifier. There'll be a diagram drawn, and then that's what we'll use to further explain the center tapped full wave rectifier. So this is the diagram that we'll be using to explain the center tapped rectifier. Now this diagram has two diodes, diode 1 and diode 2, and then it has a center tapped transformer. That's the center tapped transformer. Now, the reason the center tapped center tapped full wave rectifier requires two diodes is so that each diode conducts alternate half cycles. Each diode conducts during alternate half cycles. Now this helps it to produce output on both halves of the waveform. So each diode will take its time to conduct during the operation of the center tapped rectifier. So the diode 1 will supply current, and then it will alternate to diode 2, which will supply current, and then diode 1 will supply current once more, and that's how it will go during the operation of a center tapped rectifier. Now, due to that, we'll be taking each half cycle separately. So we are starting with the positive half cycle. We'll be taking each half cycle separately. So we'll start by treating the positive half cycle. Now in the positive half cycle, full wave of the full wave rectifier, diode 1 is forward biased. Diode 1 is forward biased. And diode 2 is reverse biased. Now let's go back to the diagram and see how that affects the flow of current. So due to that, current will flow only in that manner, in this manner, during the positive half cycle. And the wave will be in this manner. So during the positive half cycle, as that's the cycle where I've shaded, the diode is forward biased, D1 is forward biased, D2 is reverse biased, and current flows in that manner in the circuit as previously. Now during the negative half cycle, current flows in this manner. And this is because diode 1, which was forward biased in the positive half cycle, is now reverse biased in the negative half cycle. And diode 2, which was reverse biased in the positive half cycle, is now forward biased in the negative half cycle. Now we know that in an ideal diode, when a diode is forward biased, current is allowed to flow. So here, when during the negative half cycle, diode 1's current won't be allowed to go through diode 1, but current will be allowed to flow through diode 2 in the manner indicated by the black arrow. Now let's go back to where we were. So in the negative half cycle, D1 is reverse biased. And D2 is forward biased. Now note, this is very important. The direction of current through the load has not changed. Current is not flowing in another direction. The direction of current through the load hasn't changed. The only thing that has changed is the polarity of the secondary voltage. Thus, you can consider this as another positive half cycle. Like the manner in which this works is also can also be considered another positive half cycle. They are not that distinct. The only difference is that the secondary voltage polarity has been altered. Now this can be represented represented in a waveform such as, so the waveform of the negative half cycle is where the shaded part is the one below there. Right. Now when DC voltage, which is when AC voltage, which is being converted to DC voltage, goes through the negative and positive half cycle a couple of times, it results in the output voltage being in a manner such as this. So the output voltage takes on a manner such as so. Unlike the half-wave rectifier where it wasn't continuous, there were stops. Like in the half-wave rectifier, this yes, it was in that manner. There were stops, which led to the ripple effect, and it's been ineffective. In the full wave rectifier or the center tapped full wave rectifier, when D1 is doing what? When D1 is going through its positive half cycle, D2 is going through its negative half cycle. When D2 is going through its positive half cycle, D1 is going through its negative half cycle. So there's a constant supply of voltage. Which not only reduces the ripple effect but causes voltage to always be supplied. So there's always a flow of current. There's no ripple effect. There's no stop. There's always a constant flow of voltage, since when one of them is forward biased, allowing current to flow, this one is reverse biased. When D2 is forward biased, allowing current to flow, D1 is reverse biased. And so since they are alternating, there's always something allowing current to flow. Hence, that is a result in the waveform of that manner. Now, when you can draw a line in this waveform, and that will be your V average. And draw a line this waveform, that will be your V average. And then the amplitude of the waveform is your Vm. So your peak load voltage is Vm. As I recently said, your amplitude is Vm. So your peak load voltage is Vm. Now what does this mean? This means that your full wave rectifier, it will produce twice as many outputs as the half wave. As if you compare the full wave to the half wave, you can see that the full wave is producing twice as much output in the same period as the half wave. So you can see that half wave completes 1 T, like T, and it produces half, and then the full wave produces complete 1T, and that's twice the output voltage of the half wave. Now let's move into the calculations. So our V average is equal to 2Vm. As we previously described, our Vm is the peak. Our Vm is the peak load voltage. So our V average is equal to 2Vm over pi. And that also applies to our I average or our current average, which is also 2Im, which is also 2Im over pi. Now let's our V root mean square. Now our V root mean square is equal to Vm over root 2. And our I root mean square is equal to Im over root 2. So I would advise you to keep these equations in mind. Yes, remember that for, and don't get confused with the halfway rectifier. Know that for full wave rectification, V average and I average are 2Vm or 2Im over pi, and then their root mean square value is the Vm divided by the root of 2. Let's calculate for efficiency of the full wave center tapped rectifier. Efficiency of a full wave center tapped rectifier. Now, I previously stated efficiency is the ratio of output DC power to input AC power. And we know from the halfway rectifier efficiency that output DC power is I DC square times R multiplying R, and our input AC power is I, or the root mean square value of I all squared, multiplying the sum of our forward resistance and our load resistance, or the resistance of the load. Now you can do your substitutions and further deliberations, evaluations, calculations, you will end up finding out, or you end up with a result that states that your efficiency is equal to 0.8106 over 1 plus your forward resistance, 1 plus your the ratio of your forward resistance and R. Now we know that, as I've stated before, when your efficiency, when we are looking for maximum efficiency, our RF, or our forward resistance, is negligible or 0. And so if our RF is 0, and that means RF over R, or the ratio of RF over R, is 0, the only denominator we have left is 1, making our efficiency 0.8106 over 1, or 81.06%. Remember that our half-wave rectifiers efficiency was 40.5%. And that of our full-wave rectifier is 81.06%. So keep that in mind. Now let's move on to peak inverse voltage. Which I defined when I was talking about half wave. I defined peak inverse voltage as the minimum amount of reverse bias, that our diodes, in this case diodes, will be exposed to. Now in half-wave rectification, we found out that our peak inverse voltage, or PIV, is equal to Vm. That's for half-wave. So what will it be for our full-wave rectifier? So if in our full-wave rectifier, whenever one of our diodes is forward biased, the other one is reverse biased, and the polarities are always alternating, then what does that mean for our peak inverse voltage? It simply means that it will be double that of the half-wave rectifier's voltage, because just like the way the output voltage is double, so is our peak inverse voltage double. So for the full-wave center-tapped rectifier, our peak inverse voltage is 2 Vm, which is double that of our half-wave rectifier's peak inverse voltage. It is 2 Vm. So now, before we solve some examples, I'm sure you can already tell that our full wave rectifier is much more advantageous than our half wave rectifier. It's more efficient. It doesn't have much of a ripple effect, and it's simpler to. It's not simpler to work with to say, but it is a much better component to have or to use than our half wave rectifier. But it does have its disadvantages. It does have its disadvantages. So these are the disadvantages of a center tapped half wave full wave rectifier. First of all, it is difficult. It is difficult to locate the center tap. On the secondary winding of the transformer. On the secondary winding of the transformer. Now, if you were to look at it from the circuit, you would think, oh, it's relatively easy to find the center tap winding of the to find the center tap on the secondary winding of the transformer. But it's actually not. In a real life scenario, the transformer will not look this open. The circuit will not be this simplified. And it's very difficult to locate our center tap. So that's the disadvantage of the center tapped full wave rectifier. Another disadvantage is that the diodes used have high peak inverse voltage. Our diodes have high peak inverse voltage. As you can see, our PIV is 2 VM, a whole 2 times of our peak voltage. Our peak inverse voltage is incredibly high, and that is the issue, because our peak inverse voltage is the maximum amount of voltage that it's the minimum. It's not even maximum. Minimum amount of voltage that we allow during the reverse bias, and we do not want that much voltage being allowed during our reverse bias, because it disrupts the activities of the diode. Voltage is directly proportional to current. Okay, voltage is directly proportional to current, and we don't want current flowing during reverse bias. Then we don't need an increased amount of voltage during reverse bias. So that's a disadvantage. Now let's solve an example. Let's solve an example. Example 2. In a full wave rectifier circuit, the transformer has turns ratio of 1:2. So in a full wave rectifier circuit, the transformer has turns ratio of 1:2. The transformer's primary winding is connected across an AC source of 230 volts root mean square, 15 hertz. The load resistor is 50 ohms. 50 ohms. 50 ohms. Now for this circuit, we are going to determine a couple of things. Our first thing is our DC output voltage. DC output voltage. That's the whole point of having a rectifier, to input AC, output DC. So we need to calculate our DC output voltage. Then, just like we did for the half-wave rectifier, we need to calculate our peak-to-peak ripple voltage. Our peak-to-peak ripple voltage. And then our ripple frequency. And finally, the percentage ripple. How do we calculate our DC output voltage? We know that we previously found that our DC output voltage, or V average, is equal to V DC. V average is equal to V of DC, which is equal to 2 Vm over pi. Now, we do not have Vm. It is not stated in the question. So we need to find Vm for this full wave rectifier. Now, how do you find Vm? We find Vm by multiplying the root mean square value of the AC source voltage. We find Vm by multiplying the root mean square value of the AC source voltage times, or by root of 2, with root of 2. Now, as the question stated, that is 230 volts. So 230 root 2 is 325.3. So that is our V peak, or our Vm, 325.3 bits. Now let's move on to find the VDC, or the output DC voltage, VDC, which we previously stated was 2 Vm, or 2 V peak over pi, and this will give us 207 volts. 207 volts. Now that we have our output VDC, we can now move on to find our peak to peak ripple voltage, or V peak to peak. Ripple voltage, or V peak to peak. Now we know that our V peak to peak is the maximum minus the minimum. Now our maximum is 325.3, because that is our peak voltage, and our minimum is 0. Our minimum is 0. So that leaves our peak to peak ripple voltage, or V peak to peak, being 325.3 minus 0, which is equal to 325.3. Now, how do you calculate our ripple frequency? Remember, in the half wave, our ripple frequency was equal to the frequency of the AC source. So in the half wave, they give us 50 Hz at the frequency of the AC source, and that was also our ripple frequency. However, in the full wave, our ripple frequency is twice that of our AC supply frequency. It's twice that of our AC supply frequency, which means that 2 times 50 Hz, which means that our ripple frequency equal to 2 times 50 Hz. Which is equal to 100 Hz. Now, what is our percentage ripple, which is the final thing we will be finding in this example? Our percentage ripple. Our percentage ripple is our V of peak to peak divided by our V average, or our VDC. Now this is times 100%, times 100%, sorry, since it's a percentage. Now our V of peak to peak was 325.3, and our V average was 207. When you divide 325.3 by 207, you end up attaining 0.157 times 100%. 1.57 times 100%. I apologize for my mistake. 1.57 times 100%. One point 57 times 100%. this is equal to 157%. Note, this is a lot of ripple. This is still a lot of ripple. However, despite our ripple still being large, it has reduced from 314%. 314%, which was that of our half wave rectifiers ripple, to 157%. So this is a very sizable reduction in ripple. Now, how did we reduce our ripple? Or how do we reduce our ripple even further? Because despite it being reduced from 314 to 157, it's still more than 100% worth of ripple. Now, we reduce it further, just like the way we reduce that of a half-wave rectifier, by adding a capacitor. By adding a capacitor to store our charges. And reduce our ripple. Okay. So, we have completed our covering of the half-wave rectifier and the center tapped full-wave rectifier. The only rectifier that is left is the bridge rectifier. Unfortunately, we were unable to cover the bridge rectifier in today's tutorial due to time. I will urge you to include it in your personal studies. It's a very important part of rectification. But hopefully, my insight into the half-wave rectification and the full-wave rectification has been resourceful to me, and you will find it as a boost in your studies. You will use it as a boost in your studies. Now, I will not be covering the bridge rectifier today as previously stated, but I will give you a summary of the bridge rectifier before the closing. Now, the bridge rectifier, the circuit of a bridge rectifier includes 4 diodes. Its circuit includes 4 diodes in a bridge form. Its circuit includes 4 diodes in a bridge form. Now, it operates by converting both. It operates by converting both AC halves into DC. Without the need of a center tap transformer. And so here, there's no stepping down of current or stepping up as there is in the center tap transformer. Current flows through 2 diodes per cycle. Current flows through 2 diodes per cycle. So every cycle, current flows through 2 diodes. So 2 of the diodes are forward biased and 2 of them are reverse biased in every half cycle. This is more compact. It's more compact and it's also more efficient, since So this makes the bridge rectifier more compact and more efficient. However, make the bridge rectifier more compact and more efficient due to its means of operation. However, the voltage drop, previously we talked about voltage drop, where the voltage is altered by the barrier potential to drop 0.7 volts. This is what we stated this when we were covering the half-wave rectifier. That one of our assumptions was that this was an ideal diode, but in a practical diode, due to barrier potential, there will be a 0.7 voltage drop. In a bridge rectifier, due to there being two diodes have been forward biased and two diodes being reverse biased in a half cycle, the voltage drop is 1.4 volts. So in a bridge rectifier, the voltage drop is 1.4 volts per cycle. The voltage drop is 1.4 volts. Now, there's simple distinctions between a half wave, full wave, and a bridge, full wave center tap and a bridge rectifier. That in half wave, one diode is used. In center tap, two diodes are used. In bridge, four diodes are used. There is no transformer in half wave and bridge, but there is a transformer in center tap. There's no transformer in half wave and bridge, but there's a transformer in center tap. In both half wave and center tap, the voltage drop is 0.7 volts. In both half wave and center tap, the voltage drop is 0.7 volts. But in bridge, the voltage drop is 1.4 volts. And then half wave both the full wave rectifiers, both the center tap and bridge rectifiers, use the full wave. In the half wave, it only uses the half wave, as can be told by the name. It's very indicative in the name. Now, a little thing to note before I end the class is that it's filter circuits. So the filters are used in conjunction with the rectifiers too, smoothing the rectifiers conversion of DC to AC. So you should remember that filter circuits are used, and the filter circuits include capacitors, inductors, and LC and RC filters. So the inductors, they resist changes in flows, and the capacitors, they store energy and they release it between cycles. So that's all I will be. We have come to the end of this class. I thank you for being a good audience and for sticking with me till the end. My name is Daniel Kwabena Asarinyako. Daniel Kwabena Asarinyako. I am a member of GO2 and Geological Engineering 2, and I just took you through half-wave rectification and full-wave rectification. And good luck in your medicine. Good luck in your medicine. Thank you.